Yeah, welcome to the next lecture of the course Artificial Intelligence. So, in the last lecture, we have discussed about the tree search algorithm. So, basically, we have discussed that most of the AI programs can be converted to a search program, can be converted to a search problem, and then we can solve it by calling some search algorithm. So that's what we have discussed, and this is the algorithm that performs tree search for finding a solution. And here we'll be using a queue, and that queue is called as frontier. So I guess you remember this. So let us continue from here. Let us consider the original problem which we are discussing, where agent has to move from Arad to Bucharest. So if that problem, if you want to solve it by using this search algorithm, then let us see how it will work. So this is the map, given map. Let us assume this is the initial state, and this is the goal state. Now this should be solved by using tree search algorithm. Then initially the tree will have only the initial state, that is Arad. Arad will be there. Now, as per the algorithm, we should check whether this is the goal state or not. No, this is not the goal state. If this is not the goal state, this is the frontier. This is the frontier. Frontier is nothing but the queue. So queue contains only Arad. So first what we do, we remove Arad from the queue. Remove this from the queue. First check whether this is the goal state or not. No, this is not the goal state. Then remove it from the frontier and expand it. Expand in the sense identify its child. What are its child? Its child are Timisoara, CBU, and Zerinth. So let me call it as T, S, and Z. So that should be added into the queue. Timisoara, CBU, and Zerinth. This will be adding into the queue. Now Arad is already removed. So now what is at the front of the queue? T. Timisoara is there. Now again check whether this is the goal state or not. No, this is not the goal state. So remove it. Remove and then identify its child. What are its child? Its child were Lugoj. So let me call it as L. Add it to the queue. Again, continue this process. Now take CPU and expand. So basically, it goes on like this, right? So this movement. So basically, if you follow, if you observe, first we are starting with Arad. From Arad, we are expanding Timisora and CBU, and then Zerind. Then one by one we are checking. So first only we have Arad. We checked whether Arad is goal state or not. No. Then we expanded these three. Then we start with Timisora. Is this is the goal state? No. Then expand this. So that is L. Lugoj. Okay. Then we know that this is not the goal state. So expand CPU is this is the check whether CPU is the goal state. No. So expand this. So it has two child. What are they? From CPU you can go for three locations. From CPU you can go to Riminsiu, Fagaras, Oradia, and Arad. Four are there. So all these will come here. Okay. So even though Arad, even though it is already explode, still it will come here. So that is how this algorithm works. So from CPU you have we can go to Arad, we can go to Oradia, you can go to Riminsu will CA. Okay, this is Oradia and Fagaras. Okay. So this we have just explored. That's it. So now we know that this is not the destination, this is not the destination, this is not the destination. This is not yet explored. Then again come here and check whether this is the destination. No. So explore. So when you explore Zerin, again what you will get? You will get Arad and Varadia. So 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 this is Arad and Varadia. Okay, so now this is also not the destination. Again, continue with with Lugoj. Is this is the destination? No, no. Then expand. So when you expand this, you get a Yamchadia. So that will come here. So this is not the destination. Again go to the next. So all these will be in the queue. Okay. So the in the queue style you understand, right? Right. So whenever we expand a new node, whenever we expand a node, their child will be adding into the queue. And before expanding, we will remove that. Okay. So only if it is not a goal node, only if it is not a goal state, we will expand, right? If it is a goal state, we will stop. So on and so forth, the algorithm will continue uh, until it reaches the goal state. But there is one drawback with this algorithm. That's what we are discussing. The drawback is some states will be explored even multiple times, even more than one time, which is not required. For example, here you can see Arad is explored more than one time. Already Arad is explored here, but again here Arad is popping up. Again here Arad is popping up. Like that, the states may occur multiple times because it's a graph. So in a graph you can arrive at a vertex through multiple paths. So basically this is one of the drawback with the tree search algorithm. So that's what we are discussing. And so is there any way to improve the tree search algorithm? Yes, there is a way to improve the tree search algorithm. So we have an updated version of tree search algorithm which is called as graph search algorithm. So now we'll be discussing that algorithm. So this is just whatever we have discussed previously in the whatever the diagram we have drawn and shown. So that is what it shows. So if you apply the tree search algorithm for the problem of moving from Arad to Bucharest, this is how it will work. First, the frontier will have only Arad. Then we check whether Arad is the goal state or not. No. Then we remove Arad from the frontier and expand Arad. When you expand Arad, these three things you get: CPU, Timisoara, Zerin. This order is immaterial. Okay. Then we check whether CPU is the goal state or not. No. Then we remove CPU also from the frontier and we expand CPU and we add all its child to the frontier. What are its child? Arad, Agaras, Oradia, remains you will see all these things. So on and so forth, the algorithm continues until it reaches the goal state. But the problem with this approach is certain states will be explored more than once. For example, Arad is uh, popping up more than once. So again and again you have to do all those things. So whatever coming out of Arad here again it will come up. Are you getting? So unnecessarily the complexity of the algorithm, the time complexity and the space complexity will increase. So is there any way to avoid that? Yes, it can be avoided by using an improved version of tree search algorithm, and this is called as graph search algorithm. So this is the original tree search algorithm which we have previously discussed, and this is the improved version of that. So so this improved version of that research is called as graph search algorithm. Here the algorithm is almost same. Some little changes we are going to do. The it's a graph search. It takes a problem and returns whether returns either a solution or a failure. Solution in the sense a path from the initial state to the final goal state. Failure in the sense when no such path exists. So here also we have the cube frontier, which will initially contains the initial state of the problem, right? Initial and we have two queues here. So that is the important thing. With graph search algorithm, we have two queues. In tree search, we have only one queue that is just frontier. Whereas here we have two queues. The first queue is called as frontier. The second queue is called as explode, or it can this queue is otherwise called as closed. There is two names for the second queue. It can be either called as explode or it can be called as closed. Okay. So So basically, these are the two queues. The frontier queue, which will initially it will contain the initial state. Initially, it will contain the initial state alone before starting the process. And initially, the explode queue will be empty. The explode queue will be initially empty. And now, what we are doing, this is a loop. Inside the loop, we are doing all these things. If frontier is empty, then return failure. So that is the first step in tree search also. If frontier is empty, then we cannot proceed. We have to stop. Otherwise, choose the leaf node and remove it from the frontier. Otherwise, so initially, whatever the initial state, you just remove it from the frontier. Remove it from the frontier and put it in the tree, in the solution tree. So the initial state comes here. If the node contains a goal state, then return. If this state itself is the goal state, then return. That is, we have identified the goal state, that return the corresponding solution. And add that node to the explode set. If this itself is the solution, then return it as a if this itself is the goal state, then return it as a solution and add it to the explode set. Okay. Suppose if this is not the goal state, if this is so this part will be done only if this is a goal state. If the initial, if whatever in the front of the queue, initially in the front of the queue will have initial state. In other rounds, it can be some other node. If that node is a goal state, then return that as the solution and add that to the explode. Otherwise, if this condition is not satisfied, then what should you do? Expand the chosen node. So already we have removed the node from the frontier, and we have kept aside. Expand that node. So expand its child. Identify all its child. How many childs it has? Maybe it may have 2 childs or 3 childs or whatever it may be. Identify all its childs. Identify all its child and adding the resultant nodes into the frontier. And add these nodes to the frontier only if these nodes are not in the frontier or in explode set. So this is important. So we are not just blindly going to add uh, uh, these child nodes to the frontier. After after uh, after exploring, it is after expanding and identifying the child node, you have to check. What you have to check? Whether this node is already added to the frontier, whether we have to check whether these nodes are already in the frontier or not. Not only that, we should also check whether these nodes are already in the explode list or not. Okay. Only if the node is not in frontier and not in explode list, only if the node is not in frontier and not in explode list, then only we will add the node to the frontier. Then only we'll add these child nodes to the frontier. Okay. So this is how. So this is the crux of the algorithm, right? Okay. Here one more thing I would like to. There is a slight change here. See, uh, so let me explain once again, or let me just summarize it. See, basically, in case of graph search, we have two queues. One is the what you call frontier queue. The other one is the explode queue. Initially, the frontier queue will have only the initial state. So first, what we do, the frontier queue initially, uh, it will have only the initial state, and the explode queue or the closed queue will be empty. So first we just remove the whatever the element from the frontier, and we move it to the we first remove the element from the frontier, and then we check whether this is the goal state or not. If this is the goal state, then return the solution and return it as the solution. Okay, that's all. This line is over. This line is over here. These two are not combined line. Previously I said it's combined. It's not combined. If these two statements are not combined, this is a separate statement, this is a separate statement. Okay, so that's the point. If the node contains the goal state, if this is the goal state, then return as a solution. If this is not the goal state, then add it to the explode list. Now this initial state is removed from the frontier, but it is added to where previously explode is empty. Now it is added to explode because we are going to explore it. Then expand this. Then expand this initial state. So when you expand this, you will get many child nodes. We got the child nodes, but we are not going to add the child nodes directly to the frontier. Before adding, we are going to check whether this child is already available either in frontier or in explode. If it is already available in any one of these places, then we won't add this to the frontier. If it is not available in both frontier and in explode list, then we will add those child to the frontier. Is that clear? So by doing this, what we are doing in this sense, we are making sure that we are not adding a node to the frontier which is already explode or which is already expanded. So that's what here happening. Okay. I hope you are following. So basically now when this process is happening with graph search, what is happening in the sense, the the frontier, the queue frontier will contain only those nodes whose child were not yet generated. So it will have only those nodes whose child were not yet generated. Only those nodes will be here. Whereas explode will contain all the nodes which is not a solution, which is not a goal state, and also whose child were generated. In the so far whatever the nodes has been uh, opened up, in that we can divide the nodes into two categories. One, the child created. If the child is created, that will be in the explode list. If the child is not created, that will be in the frontier. So say for example, see this is a particular graph. Basically this is the graph of the our original graph of all the cities of Romania for moving from Arad to Bucharest. So this is the original graph, but this is one state. So from this, could you say I will name these vertices something A. I will name these vertices something. Say A, B, C, D. So from this, could you guess like which nodes will be in the frontier and which nodes will be in the explode list? I can see all these unshaded areas are not even they are not in any of the list. They are not either in they are not they are not in explode list, and also they are not in the frontier list. Okay, so they have just not yet they these nodes were not yet generated yet. So the path is there, but we have not yet opened it up. So from this, what we can observe in the sense, these nodes will be in the frontier list because their child were not yet generated. Whereas this node will be in explode list. Okay. So this A alone will be in explode list. Whereas D, C, and B, all these things will be in the frontier list. Okay. List is nothing but a queue, right? We can also call it as queue. Whereas if you take this here, could you identify which nodes will be in the frontier? This will be in the frontier, this will be in the frontier, this will be in the frontier. Remaining all, this will be in the frontier. Remaining all will be in the explode list because remaining all child were generated. For this node, all the childs were generated. For this child were generated. For this child were generated. For this child were generated. So they all will be in the explode list. Similarly, if you take this will be in the frontier, 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 and this will be in the frontier. Okay. Remaining all nodes will be in the explode list. Okay. Similarly, if you see this, so this diagram, so this is a different map. Say we are, so this diagram, what it shows, so it means we are exploring starting from here. So this is a node. This its child were generated, but this node's child were not generated. So all these white. basically it represents the nodes in the frontier, where the black represents the node in the explode. So this is next level of exploration. Now this node, say this node's child is created. When this node's child is created, this is one of the child, this is one child, this is one child. Now obviously, before creating its child, it will be moved to explode list. Okay. So now this is in explode list, and this three things will be in the additionally these three things will be in the frontier list. Okay, right? So so on and so forth. It continues. Similarly, if you see this graph, the difference between this and this is this node is explode, and this node is explode, and this is explode. So the child of this where the child of this were this and this. Okay, this is also a child, but it is not shown here in this diagram. uh, okay, because it is already explored, right? The algorithm will explore only those nodes which were not already in either in the explored list or in the frontier list. Why this is not coming out? Because it is already in the frontier. Is that clear? So similarly, if you see this, it will explore only this and this. It won't explore this because it is already in the explored list. Similarly, when you see this node, it will it will generate it will generate only this node because this is also generated by this node. Okay. So in this case, basically all these will be in the frontier, whereas all those black ones will be in the explode list. So basically, if a child is if a child is already generated for a node, that will be in the explode list. Or before creating a child, before generating a child, before exploring that node is nothing but creating its children. Before exploring that node, we will keep that node in the explode list. Then only we'll explore. Okay. And the new nodes, once the new nodes got generated, we will not directly add to frontier. Before adding, we will check whether the node is already in the frontier or in explode. Only if it is not in frontier and not in explode, then only we will add it to frontier. Is that clear? Okay, right. So in this diagram, the white nodes are the frontier, and the black nodes are the of explode region, and the gray or unexplored region. These are not, we have not explored. I mean, we have not gone to that extent till now, while in the process of searching, in the process of applying the tree search or graph search. Okay, so that is what it's all about. Fine. So now next what we are going to discuss in this sense, the effectiveness of an algorithm. The, the effectiveness of an algorithm is determined by these factors, whether the algorithm is complete or not. Complete in the sense, will it always provide a solution if a solution exists? An algorithm is said to be complete if it will always provide a solution when a solution exists. There are certain problems for which there are no solutions. We are not talking about such problems. If whenever there is a solution exists, the algorithm should be able to provide the solution. Such an algorithm is called as a complete algorithm. And what's the time complexity of the algorithm? And what's the space complexity of the algorithm? And does the algorithm provides an optimal solution? That is, does it provides a least cost solution? So these are the parameters used to assess the performance of an algorithm, right? Whether it is complete or not, what is its time complexity, what is its space complexity, and does it provides an optimal solution or not? So time complexity is measured in terms of b. B is the branching factor of the tree. Branching factor, here it is defined as mm, the maximum number of child a node can have. So that's the branching factor. The maximum number of child a node can have, that's the branching factor. And D represents the depth of the least cost solution. The least cost solution is available at what depth of the tree? So the tree has various depth, right? So there may be a solution at depth 3. Sometimes there may be a solution at depth 5. So at what depth the solution is available? So that is D. M is the maximum depth of the state space. Solution is available here, but what is the depth of your state space? State space in the sense this problem will maximum it go up to how much depth? Some problems may go up to depth of 100. Some may go up to 20, 30. What is the depth? Because that much we have to explore. Then we need, at the worst case, then we need to explore that much. Then we need that much space, that much time. All these things are matters. So basically we are discussing about uninformed search strategies. So these uninformed search strategies are also called as blind search strategies. They are also called as blind search strategies because we blindly search. There is no, we don't have any directions, or we don't have any guidance like how the search should go, or is we don't have any hint like if you move in this direction probably you will be successful. No such info are available, so it is called as blind or uninformed search. So these are some of the uninformed search techniques: BFS, breadth first search, which we already discussed in the data structures; uniform cost search; depth first search; depth limited search; iterative deepening search. All these are some of the uninformed search techniques. Okay. So we'll be discussing these search techniques, and also we'll be discussing uh, these techniques, applying it on that Arad and Bucharest problem. So breadth first search, I guess you remember. So we start with the root node. Initially, we start with the root node. We check whether root node is the goal state or not. If this is not the goal state, then expand. Then expand it, expand. So its children, its childs were expanded. Then start from the leftmost, start from the leftmost child node. Is this is the goal state? If this is not the goal state, expand it. We are just expanding. We are not checking here. So once checking is done, it will be shaded. Here you can see initially we are starting with A and we are checking whether A is the goal state. When A is not the goal state, it is shaded. So then expand B and C. Now check whether B is the goal state or not. No, then expand D and E. So then go to C. After this, we are not going down, we are going here because it is breadth first. First, we have to finish all the nodes in this level. Then only we'll go to the next level. Is C is the goal state? No. Then expand C, E, F, G. So C is not the goal state. Now we go to D. Is D is the goal state? No. Then expand. G becomes the D's child becomes H and I, so on and so forth. It continues. So this process continues until you reach the goal state. So this is how the breadth first search algorithm continues. So here also we maintain two, what you call, two queues. So this is the actual algorithm. So in this algorithm also we maintain two queues. One is the frontier and the other one is the explode. So the working of frontier and explode are quite similar. Frontier will be initially holding the initial state, and explode will be initially empty, and before expanding a node, we will be moving that node to the explode state. After moving it to the, that is, we will remove from the frontier and we will keep it in explode state, and we check whether it is a goal state or not. If it is not the goal state, then only we will expand it. After expanding it, again we check whether the node is already available in frontier or in explode. Only if it is not available in frontier or explode, we will add the node to the frontier. So this is the algorithm. Breadth first search, it takes a problem and it returns a solution or a failure. So the node is represents the initial state. So initially state so node represents the maybe the root node or the node of the initial state. State represents the state, initial state at which place we are. And path cost, initially it is 0. If problem dot goal test of node dot state, then return solution node. If problem dot goal test of node dot state, so this is node. If the node is the initial node, okay. If the initial node state is equal to goal test, then return that as the solution. If that is not the goal state, so most probably initial state will not be the goal state. If that is not the goal state, then what we do? Then we do all these things. But before that, there are two variables declared or two queues declared. One is frontier, the other one is explode. What is frontier? Frontier is a FIFO queue with node as the only element. Node is nothing but the initial node, starting node. Explode is it's initially an empty set. So then we loop these things. If empty of frontier, then return failure. If frontier is empty, then return failure. But initially frontier is not empty. It contains the initial state. So node is equal to pop of frontier. It's a queue. So pop means removing an element. So whatever the element in the front of the queue will be removed. In the front we have the initial node. So that will be removed. So add node dot state to explode. So whatever the node we remove, add that to explode. Add that to explode. For each action in problem dot action node dot state do. That is uh, we are exploring that node. We are going to explore that node. For each action in problem dot actions node dot state do. Child equal to child node of problem comma node comma action. So the given problem, the node, whatever the node we have taken, for that node we are generating the child. We are generating the child. Okay. And see, this is interesting, and you should also remember this because there is some relevant for this. See here what we are doing in the sense, immediately after creating child, we are checking if child state is not in explode or frontier. So we are not going to add directly. If the child dot state is not in explode or in frontier, only if the child is not in explode and also if it is not in frontier, uh, then we check whether if whether the goal state is reached or not. If problem dot goal test of child state, whether the child state is equal to the goal test or not. If that is the case, then we return that as the solution. Otherwise, if this goal test is not satisfied, then we add the child to the frontier. Okay. But this if is inside this if. This you should remember. This if is inside this if. This control will come here only if the child is not in frontier and also not in explode. After that, we are checking whether the child is the goal state or not. If the child node is the goal state, if the child node is equal to the goal state, then we return as a solution. Otherwise, we add it to the frontier. Okay. So there are two things you should note here. One is after generating a new node, we are not directly adding the new node to the frontier. Before adding the new node, we are checking whether the node is already in the frontier or in explode. Only if it is not in frontier and not in explode, then only it will be given a chance to be added to frontier. But again, before adding, we are checking whether the node is the goal state or not. If it is the goal state, then we return it as a solution. See, this goal state checking is also important. I want to emphasize on this. The reason is the goal state, please listen carefully. The goal state checking can be done at two places. One is, let us assume a tree something like this. Let us assume a tree something like this, which represents the uh, state space of a problem. Okay, this is the typical states of a problem, right? Let us say that this is the goal state. For our convenience, let us say that this is the goal state. This is the goal state. This is the initial state. Okay. So now the checking for the goal state can be done in two ways. It can be done either while generating the node or while expanding the node. Okay, so that's what I want to emphasize. Checking for goal state. Checking for goal state can be done at two places. It can be done either during generating a node. Generating means creating a node, creating a child, generating a node, or during expanding a node. Okay. So first let us see like checking for a goal while generating a node. Let us see this. So in this case, what we do in the sense, first we start with initial state is this is the goal state. No. Then we expand. Then we expand its children. Say its first child is say K, next child is L. First we expand only K. We have not expanded L. So immediately after expanding K, we check whether it's the goal state or not, even before expanding L. If it is the goal state, return as a solution. So this is called as while generating. Suppose if this is not the goal state, then add it to the, if this is already not added to frontier and explode, then add it to frontier. Then expand L. Then create this child. After creating this child, again check whether this is the goal state or not. If this is the goal state, return as a solution. Assume these three are not goal state. Now we need to expand K. So when you expand K, say you got M. There are two childs, M and N, but we are not creating both the child at the same time. First, we are immediately after creating M, you are checking whether this is the goal state or not. If it is the goal state, return as a solution. If it is not a goal state, if it is not a goal state, then check whether it is in the as per this algorithm, we check whether it is in the explode or in the whether it is not in explode or in frontier. If it is not in explode or frontier, then add it to frontier. Now create the next child N. Again, immediately check whether it's a goal state or not. If it is the goal state, return as a solution. Otherwise check whether it is not in explode or in frontier. If it is not in explode and in frontier, then add it to frontier. So on and so forth. This type of proceeding is called as what you call checking for goal state while generating a node. Actually, this algorithm follows this approach. It checks for goal state while generating a node. There is another approach. The second approach is checking for goal state while expanding. Okay, let me complete this generating a node style itself, because we are assuming this as the goal state. So now this is not the goal state. So now you expand L. When you expand L, you got G. Now check whether G is the goal state. Yes. So return as a solution. Stopped. We have not generated this. We don't know what is this. Okay, because immediately after creating a child, we check for the goal state. Whereas in the second case, expanding, checking for the goal state while expanding. In this case, what we do in this sense, first we start with initial state. Is this is the goal state or not? No. Then just create the children. Don't know checking for goal state and all. Just create the children. What are its children? K and L. Create. If K is, but this is true. If K is, then you check. We are not at all checking for goal state. We just generate K and L. Of course, we also check whether K is in the frontier and in explode or not. If it is not in frontier and explode, add to frontier. But till now, we are not checking for whether it's the goal state or not. Same thing we do for L also. Okay, we check whether L is in the previously already it is in the frontier and explode or not. If it is not, add it to frontier. So not only two child, this node may have 100 child. Even if it has 100 child, all the 100 child, we will one by one, we will check only whether it is in frontier and explode or not. If it is not in frontier and explode, add it to frontier. Only that much we do. We don't check for goal state. Okay. Then when will we check for goal state in the sense? Now this is not the solution. So again check whether K is the solution. Now remove this from the frontier and keep it in explore and see whether this is the solution. No. Now expand this. So when you expand k, you will expand all the child m n. Check whether m and n were added to frontier and explode or not. No. Then add it to frontier and explode. Add it to frontier, not to explode. Add it to frontier. Now k is not the solution. Then move on to L. Is L is the solution? No. Then keep L in explode and expand. When you expand L, you get G, say G and H. Check whether G and H is already in frontier and explode. No. Then add it to frontier. Now come to H. Now come to M. Check whether M is the goal state by keeping it in explode. No, M is not the goal state. So then expand L, M. So when you expand M, say you got O and P. Check whether O and P is in frontier and explode. If it is not, add to frontier. Then go to N. Is N is the goal state? No, N is not the goal state. Keep it in explode. Before checking itself, we'll keep in explode. Keep in explode and then check whether N is a goal state. No. Then expand. So when you expand, you will get Q and R. Okay. So now go here. Now check. So before expanding, we are checking. G is not expanded. Before expanding, we check whether G is the goal state. Yes, G is the goal state. Return it. So this is the difference between this and this approach. Is that clear? So here, when the child is getting generated, if you check for the goal state, that is called as checking for goal state while generating a node. When when you are going to create a child for that node, just before creating a child for that node, or just before going to expand that node, if you are going to check whether that is the goal state or not, that style is called as checking for goal state during while expanding the node. Actually, this algorithm follows the first approach. It follows this approach. It checks for goal state while generating a node. Right. Okay. So here is an example for breadth first search algorithm. So initially, so we this is nothing but the queue, the frontier queue. Initially, the queue contains only the start state A, initial state A, and we check whether A is the goal state or not. A is not the goal state. Then remove A from the frontier and keep it in and keep it in explode list. After keeping it in explode list, explore A, that is create its children. So when you create its children, what you get? B and C. So this is the front of the queue. This is the front and this is the tail of the queue. So now you got B and C in the queue. Now what? Take the first element from the queue, B. Is this is the goal state? No. Let us assume M is the goal state. This is not the goal state. So remove this from the queue. Keep it in the explode list and explore B. When you explore B, you get D and E. So add D and E to this. So when you add something to the queue, it will be added from the rear end, right? So D comes here and E comes here. And now what is the front of the queue? C. So again, check whether C is the goal state. No. So remove C from the frontier. So this is basically frontier. Remove C from the frontier and keep it in the explore. And explore C. When you explore C, what you get? F and G. So add F and G to the end of the queue. Now what's the beginning of the queue? At the front, we have D. Is D is the goal state? No. So remove D from the frontier and add it to explode list and expand D. When you expand D, what you get? H. So add H to the queue. Now what's in the beginning of the queue? The front of the queue, E. Is E is the goal state? No. So remove E from the queue, keep it in the explode list and expand E. When you expand E, what you get? I and J. So add I and J to the frontier. Frontier is basically Q. So IJ comes here. Now what is at the front of the queue? F. So is F is the goal state? No. So remove F from the queue and keep it in the what do you call? Keep it in the uh, expanded or closed list and expand F. So when you expand F does not have any children. So nothing will come here. Now what's the front of the queue? G. Is G is the goal state? No. So remove G from the queue and keep it in the expanded list, and expand G. When you expand G, what you get? K and L. So add K and L to the queue. Now what's in the front of the queue? H. Is H is the goal state? No. So remove H from the frontier and keep it in expanded list and explore H. When you explore H, there is nothing. There is no children for H. So nothing will be added to the queue. Now what's in the front of the queue? I. So is I is the goal state? No, I is not the goal state. So remove I from the queue and keep it in the expanded list and explore I. When you explore I, you got M. So add M to the goal state. Add M to the goal state. In this algorithm, see, let us in this algorithm we are checking for goal state while expanding. So remember this. So this checking for a goal state while expanding, while expanding the node, not while generating. Okay, so here M is generated, but we have not checking for goal state here. So just add it to the queue. Next, now what's in the front of the queue? J. Is J is the goal state? No, J is not the goal state. Remove it from the queue, add it to the expand list, add it to the expanded list, and create its children. Is there any children? No children. No, it does not have any further children. So now what's in the front of the queue? K. Is K is the goal state? No. Remove it from the frontier, keep it in expand list and expand it. There is nothing to expand. It was already expanded. I mean, it has so even if you consider G from K, but it is already there. It is already in the frontier or in the expanded list. So next, what is in the front of the list? L. Is L is the goal state? No. So remove it from the frontier, keep it in expanded list and find its children. There is no children. Now what's in the front of the queue? M. Is this is the goal state? Yes. Okay. So this is how this algorithm works. Okay. So the goal state checking can be done at two places, either while creating child or while expanding the node. So these are some of the properties of BFS, breadth first search. Breadth first search is a complete algorithm. That is, it will always find a goal if one exists. That is, its completeness property is true. And it will always find the shallowest path to a goal state. Because breadth wise we are exploring. First we explore all the levels of the tree. Before exploring all the nodes in the first level, we don't go to the nodes in the second level. So it will find a path in the shallowest. It will find the goal in the shallowest path. Okay. If tree or graph have weights, then BFS does not find the shortest length path. So this is one of the drawback of BFS. So in BFS, always we explore from the left to right. This is the style we follow. We explore the left node and then the right node, and we follow this way. But if the weights were there, assume that this path has a here the weight is 25, whereas this is 5, this is 10. Now this is a lower path. Now this path has a lower cost when compared to this path. So it is wise to explore this path first. But BFS won't do that. So BFS cannot guarantee to find a shortest path when weights are included. If the shallowest solution is at depth D and the goal test is done, see this is important. If the shallowest solution is at depth D, okay, and if the goal test is done while generating the node, and if the goal test is done while generating the node, then the time complexity of BFS is order of B to the power D. Order of B to the power D, where B is the branch factor. That is the maximum number of child a node can have. That is B. And D is the depth. Is that clear? So there are two time complexities. if if the if the goal test is done while generating the new node, if you are doing the goal test, then the time complexity is order of b to the power d. But if you are doing the goal test when the node is getting expanded, then the time complexity is order of b to the power d plus 1. Because now, say for example, we are going to do the goal test only when you are expanding the node. Say if this is the goal state, then before expanding this, you will expand all these things. So unnecessarily one more level is getting expanded. Okay, even though this will not be expanded, almost everything of this level is expanded. So it is order of d plus 1. Whereas if the goal test is done while generating the nodes, then the time complexity will be order of b to the power d. Right? Okay. The space complexity of the frontier size is also order of b to the power d. The space complexity is also order of b to the power d. So it's also same. It's also same. If the, I mean, if the goal test is done during generation, then the space complexity will be order of b to the power d plus 1. During generation, order of b to the power d. During expansion, it will be order of b to the power d plus 1. So there are some other important properties of breadth first search, which we'll see here. See, this table is quite interesting. Actually, this uniform cost search is not an advisable. Sorry, breadth first search. Breadth first search, it comes under what type of algorithm? It is uninformed search technique, right? It comes under uninformed search technique. So basically, this uninformed search technique is not a very good technique, because because if the size of the problem increases, then then the time complexity and the space complexity will increase exponentially. So that's what we are going to discuss. So uh, so this algorithm, best first I mean breadth first search, it has exponential complexity of the order of b to the power d, which is quite scary. Why it is scary, that will be known from this table. Let us consider this case. Let us assume b is equal to 10. That is, the branch factor is 10. That is, a node can have maximum 10 child. Okay, and assume that 1 million nodes can be generated by a computer. Okay, a computer can generate 1 million nodes per second. So that is the power of the computer. Let us assume we have such a powerful computer which can generate 1 million nodes per second. Okay, and let us assume that a node requires 1000 bytes of storage. Each node requires 1000 bytes, right? So uh, so when you considering these factors, considering these parameters, let us see this table. Now if you generate a tree with a depth of 2, if you generate a tree with a depth of 2, then it will have 110 nodes, worst case, because branching factor is b equal to 10. That is, the root node can have up to 10 children, 1 to 10. Okay, again again all these nodes, again all these node, each of these nodes can have 10 children. This can have 10 children, this can have 10, so on and so forth. So each of these 10 nodes can have 10 children. That is 100. 100 plus 10, 110. So it should be 111 actually. Okay, including the root. Fine. And then the memory required to store all these nodes will be 107 kilobytes. Okay, and the time required to search for any state will be 0.11 milliseconds. See, we are gradually increasing the complexity. But if the depth becomes 4, if the depth becomes 4, if the depth of the tree becomes 4 with the same branching factor 10, that is, each node can have a maximum 10 child, then the number of nodes will become this many. Okay. Here root node is ignored. If you add root node, 1 plus 1 will be added, right? And memory requirement will be 10.6 megabytes. See, from 107 kilobytes, it went on to 10.6 megabytes. and search time will be 11 milliseconds. Okay, but if the tree has 6 levels, then it will have this many nodes, 10 to the power 6 nodes. Okay, 10 to the power 6 nodes. Okay, and its time to search will be 1.1 seconds, and the memory requirement will be 1 gigabyte. Okay, so it keep on increases. When it is when the depth is 8, you need it will get to 10 to the power 8 nodes. Okay, when the depth is 10, it will get 10 to the power 10 nodes, and search needs 3 hours. See how much difference. For when the depth is 8, the search requires only 2 minutes. Worst case, it's quite okay. But here, for worst case, the search becomes 3 hours, and memory requirement it becomes 10 terabytes. 10 terabyte. When the depth is 12, for the worst case search, it needs 13 days. Needs 13 days, and memory requirement becomes 1 petabyte. Okay. When the depth is 14, the number of nodes will be 10 to the power 14, and the time requirement will be 3.5 years. See, 3.5 years, and memory requirement will be 99 petabytes. When the depth is 16, the number of nodes will be 10 to the power 16, and the time required will be 350 years. Okay. So the point here we are making is only a small, only the problem which is of smaller in nature can be solved by using techniques like uninformed search techniques. If you apply uninformed search techniques to any of the real world problem and say that the solution is available at 14th level or at 16th level, then probably we will not get the solution at all, because the search is going to continue for 3.5 years or 350 years, which is unrealistic, right? Okay. So from this, not only this, from this you can also understand the what you call understand the challenges of AI. From this you can also understand the challenges of AI. See, this is a small search problem which the solution is available at a deeper level, that's it. And it has, and the branching factor is only 10. But still, if the solution is at 16th or 17th level, then the best computer with such a high processing speed, it needs this much time. So here we are not talking about any supercomputer. We are talking about personal computer with a very good configuration. Okay, but still it takes this much time, right? So this is what the what you call the learning we got from this. Okay, fine. So now we move on to a next type of algorithm, which is called as uniform cost algorithm. Basically, this is also one type of uninformed search technique. Uniform cost search technique is also it is also one type of uninformed search technique, and also it is very similar to breadth first search. It is also very similar to breadth first search, but it is more refined. It is more refined, and and depending on the weight or depending on the cost, it chooses an ideal path. Okay, so basically this is a modification of BFS. So this is a modified version of BFS, and we got a new algorithm which called as uniform cost search, which works with any step cost function. See, the breadth first search does not see the cost. It does not mind about the cost. It always explode the node in the leftmost child, then the next child, so on and so forth. Like that, it continues. Whereas uniform cost search, it is a step cost function. So in all other aspects, it follows the breadth first search, but it explores the path which is of least cost. It explores the path which is of least cost. UCS expands the node n with lowest summed path cost. Okay, with lowest summed path cost. It's not level cost. It's the lowest summed path cost. So to do this, the frontier is stored as a priority queue. Here the frontier is a priority queue. In the breadth first search, the frontier is just a queue. For example, a node A has three childs B, C, and D. Okay, say the cost of reaching A to B is 10, A to C is 5, and A to D is 2. Then, in case of if it is a breadth first search, it will store something like this: B, C, and D. It will always store left to right. So this is the front of the queue, and this is the rear of the queue. It don't it don't mind about this cost. Okay. So this is the case of BFS. The frontier will look like this. But the same frontier in case of uniform cost search, the frontier will be D, C, and B. This is the front and this is the rear. Why? Because one with the least cost it will keep first. So here, which is the least cost? D is the least cost, so that will come first. C is the next least cost, and D is the highest cost. Okay. So here the queue is sorted based on the priority. So based on the cost. So this is a priority queue. So okay. So this frontier is a priority queue. So here the frontier is stored as a priority queue. The goal test is applied to a node when selected for expansion. This is also another difference. In case of our original algorithm for breadth first search, if you recall, the goal test is done during generation. In case of breadth first search, the goal test is done during generation in the actual algorithm. Okay, whereas here the goal test will be done only during expansion. Will be done during expansion itself. Also, a test is added if a better node is found to a node on the frontier. Also, a test is added if a better node is found to a node on the frontier. That is, mm, so basically these 2 points are actually same. So we perform the goal test during expansion. So during expansion, what happens in the sense, maybe multiple paths may be available to the goal state, but we differ until we expand that node. Okay, we are not going to hurriedly say that this is the goal state. Okay, we'll discuss that with an example, then it will be more clear. So this is the algorithm, uniform cost search. It takes problem as the input, it returns a solution or a failure. So all these initial parts are same. The frontier, which is a priority queue, which initially contains the initial state. Explode is empty. Loop, if frontier is empty, return failure. Otherwise, pop the first element from the frontier. Basically, it's a queue, that is PQ, the first element from the frontier. Now, frontier is a priority queue, which is sorted based on the path cost, right? If problem goal test of node state, so whatever the node you have popped out, if that is the goal state, then return as a solution. Otherwise, if that is not the goal, then add it to the explode state. Okay. Then start exploring that node. Create its child. Create the child node, and then check whether the child is not in explode or frontier. If it is not in explode or frontier, then add it to the frontier. Okay. If it is already in the explode or in frontier, then here one check we are doing. Please try to understand this. If it is not already in frontier or explode, add it to frontier simply. If it is already in frontier or explode, then else if child dot state is in frontier with higher path cost, assume that a particular node, say k, it's already in the frontier. Now when you explore a node, yes, you also get k. Okay. So uh, now if it is not in frontier, we will add it in the frontier. If it is not in frontier and in explode, we'll add it in frontier. But if it is in frontier, then also you should do one more test. What is that in the sense? Check the cost of reaching k via s. Assume the cost of reaching to k via s is 6. But assume this already here k is there with the cost of 12. Okay. In this situation, this k should be replaced with this k, because this here k can be reached with the least cost. So that should come here. So that is what this statement says. Else if child dot state in frontier with higher path cost. So this child is already in the frontier with higher path cost. Yes, it is higher path cost. Then replace the frontier node with child. Replace this k with this k. Okay. So replace this k with this k. That is with the cost of 6. That is what it says. So that's the algorithm. So here is an example given, which I think this example will clarify the concept of uniform cost search. So it's just one part of the original graph, Arath to Bucharest graph. Only this part of the graph. With this, we can explore. So now let us see how uniform cost search will work on this. So initially, the frontier will have what? Frontier will have CBU. Frontier will have only CBU. Okay. So as per the algorithm, what you have to do, you have to remove that from the frontier and keep it in. The first step is to remove this from the frontier and keep it in explore. Keep it in explore. Okay. Check whether this is the solution or not. This is not the solution. Let us assume we want to reach Bucharest. So this is not the solution. Then expand. Then expand means this is a uniform cost search algorithm. It will expand only the least cost path. So from CBU you can go here. Reminsu will see at the cost of 80. You can go to Fagaras at the cost of 99. So it will explore which one? It will explore this one. Reminsu will see. So Reminsu will see is the child. It's identified. Check whether this is already in the frontier and explored list or not. No, it's not already in the frontier and explored. So add it to frontier. So Reminsu will see you will be added to the frontier with the cost. With what cost? With the cost of 80 from the initial state. Like that it is added. Okay. Now what the algorithm should do? Now algorithm again it will come back and remove the first element from the frontier. So this is the first element. So remove this and this will come to explode or V, that is remains will see 80. Okay. So the path cost is 80, right? Then it checks. Uh, sorry, 1 minute. Let us go through the algorithm. Uh, so if pop up frontier, that is we choose the lowest cost node in frontier. Okay. If gold test, yeah, we are choosing from frontier only, not from anywhere else. Okay, fine. So we are correctly going. So then what it does? Then it will explore. Then it checks whether this is the goal state or not. This is not the goal state. So explore. So when it explores, it has only one path. That is Pitesti. That is Pitesti. So it gets Pitesti. So Pitesti now Pitesti, it is reaching Pitesti at the cost of what? You have to sum up. It's not just 97, 80 plus 97. So what is 80 plus 97? 177. With the cost of 177, it can reach to Pitesti from where? From CBU. Okay. So that's what the algorithm says. Okay. So now add this. So now add this to the, before adding, check whether this is already in the explode and frontier or not. So we check that. So if it is not in explode or in frontier, we add it to the frontier. Okay. So that's what we do. Okay. So add it to the frontier. So this will be added to the frontier. So now Pitesti is added to the frontier. Okay. With the cost of 177. With the cost of 177, it is added. Okay. So there is a small correction. So we have something we have left out. Okay. So let us follow this order. See, So this is how the algorithm actually works. So initially the frontier contains CPU. That is fine. Okay. This is frontier. Frontier contains CPU. Okay. Let us assume, or let us say this is the front of the queue. Okay. We'll add here, right? So we check whether this is the go. So we remove this from the frontier. Remove this from the frontier and add it to explode. This is explode. Add it to explode and then explore CPU. So when you explore, we explore both the child. Okay, it's not that one child, we explore both the child. So one is Remensible CA, the other one is Fagaris. So what is the cost of Remensible CA? 80. This is 99. Both will be added here. Okay, both will be added, but how it will be added? This is a priority queue. Please mind it. So it will add based on the cost. So whichever the least cost, that will be added at the front of the queue. So 19. So Fagaris will be added here with the cost of 99, and then this Remensible CA can be reached at the cost of 80. So it's a priority queue which is sorted based on the path cost. Okay, so that's the logic. Now, so now what we do? We check this is not a solution and we expanded this. So now again continue. Now again remove the front of the queue. Front of the queue is this Remensible CA. So bring it to here. Remensible CA 80. Okay, and explore. So Remensible CA has only one child, that is Pitesti. So let us say this is Pitesti, can be reached at the cost of 97. So the total cost is 177, right? 97 plus 80, which is 177. There is nothing here. Remensible CA does not it has only one child. Okay. Now, so now what is the cost of reaching? Now RV is removed. No more RV is not in the frontier. It is removed. Now what's the total cost of reaching Pitesti from CPU? It is 177. So that will be added here. So that will be added here. So Pitesti can be reached at the cost of 177. But this is a priority queue. This should be sorted based on the path cost. Now which cost is minimum? Fagaris cost is minimum. So now the frontier queue will look like this. Pitesti can be reached with the cost of 177, whereas Fagaris can be reached with the cost of 199. Like that it will be there. Okay, I think you are following. Now, so in the next round, so this is the, say, this is the front of our queue. Okay, I have written front there, but this is the front of our queue. So this is the front of our queue. So from front, remove. So what is there? Fagaris is there. Remove Fagaris. So Fagaris is removed and move it to explode list, because now we are going to explore Fagaris. So remove Fagaris and move it here. Fagaris at the cost of 99. It's not 199, it's 99. Yeah, it's just 99. Okay. So we can reach Fagaris. So from CPU we can reach Fagaris at the cost of 99. So expand Fagaris. So when you expand Fagaris, you got Bucharest, which is the solution. But we are not going to check for the goal state, because as per the uniform cost search algorithm, the the goal test should be done while expanding mode. While expanding Bucharest only, we are going to do the goal test. We have just generated Bucharest. Okay. And what is the cost? 211. 99 plus 211. What is 99 plus 211? 211 plus 99 is 310. That is at the cost of 310. So at the cost of 310, it can reach what you call, at the cost of 310, you can reach uh, Bucharest. Okay. So now Bucharest, check whether Bucharest is in the explode list or in the frontier. No. So then add it. So when you add it to the frontier. Okay. So Booker already what is there? Already Pitesti is there. Okay, Pitesti can be reached at the cost of 177. Bucharest can be reached at the cost of 310. So that is what here. Okay, but still, even the Bucharest came, we have not done the gold test. Okay, now in the queue, which is the one with the least cost, this is the one with the least cost. So remove this and move this to explode list. So Pitesti will come into explode list. That is, it will come here. Okay, so yeah, so Pitesti will come to the explode list. Okay, and from Pitesti there is only one path to Bucharest. Okay, so Bucharest can be reached uh, from Pitesti. It is 101. So 177 plus 177 plus 101 is 170 278. Okay, so there is another cost for Bucharest. So now we got another cost for Bucharest with 278. So again, you check whether Bucharest is already in the frontier or in explode list. It is already in frontier, but whatever already in frontier, that cost is higher. So in that case, it should be replaced with this cost. So this Bucharest 310 will be replaced with Bucharest 278. Okay. Now in the next step, what we will do? Now now the queue contains only Bucharest. So we remove Bucharest and we keep it in the what do you call, in the explode list, and then we check whether this is the gold state or not. Yes, this is the gold state, but now we are going to take which path? 278 path. That is we are not going to take this path, we are going to take this path. Is that clear? So this is how uniform cost search algorithm works. So uniform cost search, actually it always finds an optimal solution, whereas breadth first search will not find an optimal solution. So it is similar to a Dijkstra algorithm, and it requires that the step cost should not be negative. Then only it will work. With negative, if negative cost were introduced, then it may lead to some kind of failure. Okay? And also it should not include any path with null cost, or any path with zero cost. So if there are any path with zero cost, then this algorithm may create some infinite loop without arriving at any solution. At least there should be some minimum positive cost associated with each path. Okay, then this algorithm will be complete. Suppose if there are zero cost paths were introduced somewhere in between, then sometimes this algorithm may not be complete. Right? Okay. So generally it is complete. If these conditions are satisfied, it will be complete. Otherwise, it may not be complete. So there are some other interesting facts about this algorithm. Coming to the time complexity of this algorithm, the time complexity of uniform cost search is order of b to the power 1 plus c star by epsilon. Why is that, you may ask? The reason is, let us assume that c star is the cost of the optimal path. So in this case, this is the optimal path. Let us assume c star is the cost of the optimal path. Okay, and let us assume the minimum cost, and let us assume the step cost is epsilon. Each The cost of each step is epsilon. Okay, then it has this many steps. Right? And and we are finding the solution. When How we are finding the solution? We are finding the goal test is being done during the goal test is being done while expanding the node. Okay, so if you see normal breadth first search is also the time complexity is order of b to the power d, or it is order of, worst case it is order of b to the power d plus 1. Okay, so in this case, instead of d, we don't know the depth is not it is not going to choose the shortest depth. In this algorithm, if you see, this is the shortest depth, only 2, but this is 2 3. So here the algorithm is not optimized based on depth, it is optimized based on cost. So that cost we are converting to depth by c star, by doing c star by epsilon. Okay, so instead of order of b to the power d plus 1, it becomes order of b to the power 1 plus c star by epsilon. Okay, so that is the time complexity. So that is how this number arrived. Fine. So let us stop here for today's session. Thank you.